So in our previous assignment, we talked about the law of conservation of momentum. And essentially what that is a collision between two objects. So we're just going to extend yesterday's conversation about the momentum before an event equals the momentum after event into what are referred to as collisions. And a collision is exactly what it says it is. It's two objects that are colliding together. If you've ever gotten in a car accident, you have been in a collision. So there are actually two types of collisions that we can break everything down into. The first type of collision is called an elastic collision. And an elastic collision is literally when two objects will bounce off of each other. Okay? Now, we kind of make the assumption that they will return to their original shape, which is not always the case, particularly if you have two cars colliding like we have right here. Okay? They're probably not going to return to their original shape. Okay? But we make the assumption that they do. Okay? So, you can kind of see that if you look at the momentum total in this particular object before the collision and the total momentum after the collision, okay, you can see that the total momentum before here is 20,000 and before here is minus 60,000. And you just got to pay attention to the direction. Okay, that's why the 60,000 is negative. But then if you look after the collision, you see right here, this number is changing to minus 40. So 20,000 plus 60,000, or minus 60,000 is minus 40 to begin with. And if this truck stops, then we are following the law of conservation of momentum. Okay, now, this is not a huge issue right now, but it becomes an issue in the next chapter. Okay? So in this particular one, there is no loss of kinetic energy. Now, in this type of collision, okay, our momentum equation that we developed yesterday really does not change. Okay? Our law of conservation of momentum is still M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. So this equation right here is really the equation for an elastic collision. So you already have it on your note card. You might want to just add to your note card that this is an elastic collision. Okay? Now, how does this work in a problem? So here's a problem. If you need time to write it down, just pause the video and write it down. You're going to have to pay attention to directions in these types of problems because as we saw the other day in class, if you forget a negative sign, it makes a difference. Okay, so what we have is a truck, a 1,500 kilogram truck traveling to the east. Okay, and east in our case is our positive direction. And then we have a 1,300 kilogram car traveling to the west, and that is the opposite direction. So one of these two has to be negative. Okay, if we keep our sign conventions the way we have been all year, then east is positive, west is negative. So if they have a collision and they separate, okay, and that's kind of the key word for elastic. They bounce off of each other. And we know that the final velocity of the car is to the east. We want to know what the final velocity of the truck will be. I will tell you that it is very important that you keep track of everything by writing givens down. Bookkeeping with givens becomes important. So the mass of the truck is 1,500 kilograms. The initial velocity of the truck is 13.3 meters per second. the mass of the car is 1,300 kilograms, okay, and the initial velocity of the car is minus 8.88 meters per second because it's traveling in the opposite direction. Now, we know what we want to know is what is the final velocity of the truck. So the final velocity of the truck is going to be what? Okay, knowing that we have the final velocity of the car, okay, which is to the east, which means it is a positive 14.86 meters per second. Okay, so getting all of those directions is important. So then, because this is an elastic collision, okay, our equation becomes m mass, and you can use m1 or you can use what they are. So the mass of the truck times the velocity of the truck initial plus the mass of the car times the velocity of the car initial should equal the mass of the truck times the velocity of the truck final plus the mass of the car times the velocity of the car final. Okay? Now, we are looking for the final velocity of the truck. You can kind of do this a number of ways. The U of M would like you to solve for one final equation. I'm not so great about that at this particular time. I would just fill in numbers, but we are going to have to get to the U of M's version of a wild equation. Okay, so I'm just going to fill in what I know. Mass of the truck, 1,500 kilograms. Velocity of the truck initial, 13.3, plus the mass of the car, 1,300 kilograms, times the velocity of the car, minus 8.88, equals the mass of the truck, 1,500 kilograms, times the velocity of the truck final, that's what I'm looking for, plus the mass of the car, 1,300 kilograms, times the final velocity of the car, which is a positive 14.86 meters per second. Okay, now, you can do the math, okay, and solve. So I'm not going to waste a lot of video time solving this. Your final velocity of your truck, if you haven't calculated it, you should pause right now. Drum roll, is minus 7.27 meters per second. Now, that minus is significant because that's a direction, and so that basically this is moving to the west after the collision. Okay? So, and that becomes important. And then what you need to realize is, hey, this right here is just the initial velocity right after the collision. So it's the final velocity when they collide, but then they're probably going to come to rest due to outside forces. Okay? So that's how we would handle an elastic collision. And again, pay attention to direction. That is ultimately going to be your demise if you don't do that. Okay? Now, the second type of collision is called an inelastic collision. And an inelastic is when two objects basically collide and they're going to stick together. So, elastic, bouncy, like a rubber band. Elasticity, bouncy. Inelastic, not bouncy. Okay, so now the objects are going to stick together. The key here is that when they stick together, the final velocity remains the same. So this is kind of a silly little video thing that I found, but it kind of demonstrates it. So you have a big fish at rest, he swallows a little fish, and then they move together at the same final velocity. Kind of silly, but it works. Okay, so the equation for this inelastic collision, since the objects stick together after the collision, this final velocity and this final velocity are the same. So V1 final equals V2 final. Okay? So they have the exact same final velocity. So because those two velocities are the same, then this equation becomes m1 v final plus m2 v final on the product side here, or this side. And so we can take these two, since they are the same, and we can factor that out. So V final times M1 plus M2 would equal basically what we have over here. M1 V1 initial plus M2 V2 initial. So this equation should go on your note card as the equation for an inelastic collision. Okay? So put that on your note card as well. So now, how does this work? So here's another problem. Okay? A car is moving down the highway and it has a velocity of 32 meters per second. So again, we have a mass and a velocity. Okay, when it bumps into the car ahead of it, okay, which has a mass of 800 and a velocity of 25 meters per second. So paying attention to wording, what's happening is both of these cars are moving in the same direction. So I have a smaller car in front, okay, so like a bug, okay, and I have a larger mass car behind, okay, and the velocity of this car is 32 meters per second, and the velocity of this car is 25 meters per second. So that means that this car could, not have wheels. Okay, this car could overcome this car and crash into it, apparently without wheels. Okay, so the two cars are going to stick together, okay, but since they're both moving in the same direction, okay, they are both going to have the same positive velocity, okay? And you could flip this and say they're both moving in that direction, but this is the way I chose my world, so that's how we're going to do it. Oops, that's not what I wanted. Oops, now I'm screwed up. Okay, sorry. Don't know what just happened there. Okay, so I'm going to keep moving in that direction. So again, you have to pay attention to what your masses are. The mass of this car was 1,250 kilograms. The velocity, or the mass of this car was 875 kilograms. So because we stick together, our equation is now M1 V1 initial plus M2 V2 initial equals V final times M1 plus M2. And this would not be a hard equation since we're trying to find V final. Okay, we could divide by M1 plus M2 right away. and divide this side by M1 plus M2 right away. So our V final is going to be essentially this side of the equation, which I am just going to fill in. So M1 is 1,250 kilograms times the speed that he is going, 32 meters per second. And then we're going to add 875 kilograms times 25 meters per second. And all of that is going to be over the two masses added together. Okay, now you can pause the video and do the calculation. But your final velocity should come out to be 29.1 meters per second. Okay, so the velocity kind of ends up in between the velocities of the two cars. The lead car right here was going slower. This car was going faster. So the velocity kind of ends up somewhere in between them. So that is elastic and inelastic collisions. You now can do the problems that are on the worksheet.